All right, welcome back. And again, we're still looking at how to make this inference on the population, right? And we could focus on the mean or whatever parameter we wanted to. Mean is going to be kind of the easiest one for us to begin our discussion of. But again, there's this guiding question: how do we make this inference so that with the samples that it makes sense? And then the credibility piece we already discussed kind of in the last video. Okay, so as we look at the first question there in blue, right? We want to remember the principles of experimental design, right? There was the controlling lurking variables, randomization, and then using a large enough sample. And that large enough sample is a little ambiguous, right? What is large? Okay, we'll define large in different ways here coming up. But to begin, I want to take a peek at this Excel example one. Okay, so here it is, and it is, I'm going to kind of talk you through it and you can follow along if you wish, but it is the experiment where we're imagining rolling a six-sided number cube or a dice, or a die. I'm sorry, die is singular. Um, so if you can imagine rolling a single number die, okay, so it's six-sided number cube with 1 through 6 on each, on the sides, one number per side, and they're all equally likely, etc. So then what do you think is the probability of rolling a 6? Well, okay, given that one of the 6 sides is 6, I'm going to say that the probability is 1.6666. So we're going to call this our population proportion. So out of all the rolls, we would expect 1/6 of them to be a 6. Okay, so now do you expect to see this when you roll? Okay, this is a question that I'm not going to answer because this is individual. So just take a minute and think for yourself. Do you expect to see 1 out of 6 rolls be a 6 every single time? Why or why not? Okay, so here, normally I do this in class with actual dice, but well, we're not in class for this video. So what we're going to do is we're going to simulate this. Okay, so over here you can see I have the group data and then I have some calculations going on in the background here in Excel. So what I'm going to do to simulate that rolling idea is just do rand between and then 1 and 6, and that would represent a given side of the die that's rolled. Okay, and so okay, on one roll I got a 4, and my proportion here is set up to only count the sides that are 6s. So as I roll some more, let's just do a few more. Okay, so you can see I got a 6 on this roll, but that's the first roll is a 6 out of what, 1, 2, 3, 4, 5, 6, 7. So this is 1/7. Okay, so 1 out of 7 rolls is a 6, and I'm just going to carry this experiment on for a while. Okay, and we're going to take a look at all this. Okay, so I made a graph showing the sample proportion over time. And so you can see for this experiment, okay, where I did it, what, 63 times or so, that the proportion oscillated based on the number of rolls that I did. Okay, and eventually I ended up at at 11%. Okay, which was a little different than the 16%. Okay, now let's say you do your experiment and you get something a little bit different. So I'm going to do Fn F9 on my computer. Okay, so there I got something a little bit different. So I just repeated this and now I'm at approximately 14%. Okay, still under the 16%. Okay, and you can continue doing this, and this time, whoa, I got lots of 6s. Okay, 21% of the time I got 6s. Okay, so with this, why am I not seeing the 1/6? So that's one question to think about. But then also, okay, so I did it, what did I say, 63 times? What if, does it matter if I do it 100 times? 1,000 times? 1,000,000 times? Because I mean, it's just rows in Excel. I could extend the table if I wanted to. So does that matter? Okay, would I see the 1/6 at some point? Okay, and that's kind of where we want to come back now and talk about kind of the key takeaway. And that is that we don't see the proportion, or in this case, the proportion that we expect. We don't see the parameter that we expect in the short term, but as we take more and more samples, it should get closer to what we expect. Okay, so I'll just capture that here. And so I've captured that idea here. Okay, so in the short run, we're probably not going to hit that mark that we want, but if we get a larger sample or increase the sample size, that's the equivalent idea, we should get closer to the actual value. Okay, and that idea is a direct result from what mathematicians and statisticians have called the law of large numbers. Okay. Now this is the technical language. Okay. As some of you are seeing this and like, oh my God, what are we doing? But it's okay. Let's just kind of walk through this. So n is the size of the sample, and then x1, x2, these are all what we call independent and identically distributed random variables. So that just means these are repetitions of an experiment where we don't know the outcome ahead of time, right? That's why we call them random variables. And when we use the language of independent and identically distributed, that just means each outcome isn't influenced by another, okay? And they are all from the same set of possible outcomes, okay? So in this case, from the number die, right? They're all rollings of the same number die, okay? And then we also have to have finite population mean, okay? And then all this is saying is that the population means, as we look at them, kind of a series of the population means, they would approach our theoretical our sample means approach our population means. Okay, so sample means approach population mean. Okay, and technically, what we were doing, we were working with p hat, so it would just be p hat approaches our sample proportion approaches our population proportion p. Okay. Now, when we're working with the law of large numbers, we need to verify a few things, right? Because this is a theorem. It has hypotheses and conclusions. So we need that the xi's, so our repetitions here are IID, okay? And then we also need mu, our population mean, to be finite, okay? Number two is usually satisfied trivially for us. There are cases where we do have to worry about it, but we're fine in our class. Okay, so here are a couple quicker examples. Okay, we know that human average body temperature is 98.6 degrees Fahrenheit, and then if you were to get a sample and measure their body temperature, what does the law of large numbers say about the sample mean body temperature? Well, if we say T is average body temperature, then the average of the however many we have in our sample should approach 98.6 degrees Fahrenheit. Okay, that's our population mean. Okay, and similarly, if we just change our experiment to be flipping a fair coin, and a fair coin is, one side is heads, one side is tails, and it's equally balanced, all that good stuff. If we're thinking about the proportion for heads flipped, so p hat is going to be the proportion of heads flipped. Okay, we would expect this proportion to approach 1/2, right? Because there's two possible outcomes, and one of the two is a heads. So these are kind of quick examples of the law of large numbers, but the idea with law of large numbers is that the sample mean should approach the population mean as long as we have this IID feature where we have the observations being independent and identically distributed. In the case of the latter example, we're flipping the same coin, and in the former, with the first example, we have humans, then one human hopefully doesn't, or one human's body temperature isn't influenced by another human's body temperature. And I mean, please don't go and think like anything about colds or anything, because that's outside of our view here. Okay, so law of large numbers. One nice way to be able to make an inference about a population mean.